This screencast will be a introduction to enzymes and should be a review from Biology 1. We're dealing with essential understandings or essential knowledge 4B1 here. Text references pages 96 to 100. So we're going to look at enzymes' role in reactions and then the relationship between substrate, enzyme, product, active site, and this induced fit concept. So in the previous screencast, we talked about free energy, right? And then over the progress of the reaction. So every chemical reaction that's happening in the cell has a free energy component to it, and most reactions will not take place just kind of spontaneously. You're not going to have these reactions happening. You need some sort of catalyst to help help those reactants become products. So as we see here, these are relatively stable reactants here. A is bonded to B, C is bonded to D. These bonds, of course, represent, again, potential energy, and these bonds are not just going to break on their own. But what we want to do is these reactants, in general, are going to be converted so reactant AB is going to be converted into product AC, and reactant CD will be converted into product BD here. The line represents, the curve on the graph then represents an increase in free energy of the system, so this being the system in reference here. And so we have to first sort of go up this energy hill here. This energy hill is called the energy of activation, or E sub A, energy of activation. Right? And you need to put a little bit of energy into this system to get these bonds to now break. You're going to stress them in some way. And then once you reach this transition state, they become sufficiently unstable that these bonds will break and these bonds begin to form. And as you do that, these bonds, this AC bond and this BD bond, are at lower free energy than the bonds between A and B and C and D of the reactant. So our change in free energy over here is, of course, negative. We have a net negative delta G over there. So this just does not happen. This energy of activation, this uphill here is not just going to spontaneously happen. This would be like saying that something would just spontaneously kind of burst into flames, right? But that's not going to happen. You need to sort of add a match there or some sort of energy in there. But once you get that going, it might go to completion. So if we look at these curves here again, we notice that on this graph here again we're measuring the relative free energy over the progress of the reaction here. And our reactants are starting here and our products are ending down here. So this is a negative delta G that we're ending with here. And here is our E sub A without an enzyme. And you notice that that activation energy is higher than when we add an enzyme. So this E sub A with the enzyme right here, I mean, this difference helps us get to a definition of what all enzymes do. And enzymes here, yes, are catalysts to reaction, but the strict definition of what an enzymes do is that they lower the E sub A, or the energy of activation, for reactions. And by lowering that E sub A, it makes it more likely that those reactants will then be converted into products. So again, the definition of enzymes is that they lower the activation energy, or the energy of activation, for reactions. I want to point out something new here on this slide that we've not seen yet in any of these screencasts here, is that down in this lower right, there is a link to a Semanis animation, and if you click on that link, then it should take you to a video. I'm not sure if it'll work, but I've also included the URL on the Blackboard site just below this screencast. So take a look at that, and it will animate, and another little tutorial there for you to take a look at in terms of this energy of activation concept. Now, enzymes are going to be lowering the energy of activation, and the way that they do that is by colliding with a substrate. So in this diagram here, actually let's look at the title of this. The substrate must be complementary to the properties, the shape and charge of the active site of the enzyme. Right? And there's an induced fit between substrate and enzyme at the active site. So again, here we have our enzyme molecule. We're going to start over here. Right? And so this is the enzyme. And this right here is referred to as the active site of this enzyme. So this enzyme, right, the three-dimensional aspect, the three-dimensional characteristics of this enzyme are important. And we're going to be talking about this more later. But the three-dimensional characteristics of this enzyme are important because it's the shape of this active site, the three-dimensional shape of that active site, where the substrate is going to fit. Right? And by fit, we mean that the shape of this is complementary to the shape of the active site. So substrates fit with the enzyme at the enzyme's active site. Substrates fit with the enzyme at the enzyme's active site. So as this enzyme is moving through solution, it's going to collide with these substrates, and you get this brief enzyme-substrate complex forming here. So what we want to notice here, and this is hard to see in this static diagram. So again, I'll draw your attention to the lower right here. There's an animation, this McGraw-Hill animation, which is also on Blackboard. Going to that animation, it will make this sort of animate for you and not be as static. But what we want to notice is that this enzyme shape here is not exactly the same as the enzyme shape here. So what's happened is, as this enzyme collides with the substrate, the enzyme changes its conformation, its form, its shape. Right? So when the enzyme changes its conformation, it's binding with that substrate. And in this case, that change in conformation is going to be stressing that bond right there. Right? And that enzyme changes its shape a little bit. We add this little water here, more on that later. And we end up getting this enzyme now breaking that bond between those two submolecules there. Right? And then there's going to be this next slight change in conformation as well, and then the products are released from the enzyme, and that enzyme then returns back to its ready state, able to catalyze another reaction. Now, of course, this whole cycle here is happening relatively quickly within the cell, but is dependent upon these enzyme molecules moving in a solution, these substrate molecules moving in a solution, and this is indeed what's happening. Inside of a cell, outside of a cell, these are all solutions. So again, this whole enzyme reaction here can be summarized thusly. The enzyme plus a substrate yields a brief substrate-enzyme complex, which then yields the enzyme and the product back again. So this general formula is descriptive of what's happening in this diagram. So here I'm just kind of statically showing you in blue the enzyme. This, it's hard to see that, so let me see if I can just change this in color here. So here, this represents the enzyme. This pocket right here is the active site, and this is then the substrate. And so what we see is that as that enzyme collides with that substrate, you're going to get this little change, this slight change in the conformation, right, of the enzyme. Right? This change in conformation of the enzyme is referred to as an induced fit. Induced fit. This is the concept of induced fit, where as the enzyme approaches the substrate, you get this substrate-enzyme complex, right? And the enzyme changes its conformation slightly, right? It's induced, right? So the substrate colliding with the enzyme is inducing this fit, is helping that fit be a little bit more tighter, better, higher affinity for the substrate and the enzyme coming together. So again, this induced fit is the changing of that enzyme conformation. One final diagram here to represent what's going on here. At the bottom, we have our enzyme. Here's our active site. Here is our substrate. And as the enzyme and substrate come together, they form this substrate enzyme complex right here. The enzyme, this is an induced fit, changes its shape just slightly. The bond is stressed and broken. These then are our products over here. And then our enzyme regenerated down here. I want to call your attention to both of these examples I've shown you here involve a breaking down of a more complex molecule to two simpler molecules, but that this reaction can also go the other way. So we can put these arrows like this, where I could take two smaller subunits, use an enzyme to drive the reaction in the opposite direction as well, and I could then get two or more things to come together and form a larger there. So enzymes are doing reactions, not just breaking down reactions, but also building up or synthesizing reactions. And this is indeed what's happening inside the cell at many different levels, at in various places throughout the cell. So there's a quick enzyme introduction and review.